Hi and welcome back. In this 7 minutes section, we will have a look at compaction. What is it, how do you enable it, and how do you check the space savings? Compaction is a feature that saves aggregate space. Basically what it does is it will try to group blocks that are smaller than 4 kilobytes together into single 4K blocks so as to save space. For compaction to work, the volume should be thin provisioned. It works at the aggregate level, and compaction does not change logical data. So it simply saves space at the physical level. By itself, compaction generates no performance overhead. However, if blocks that were not compressed by inline compression are compressed by compaction, then that will take up to 2% of CPU cycles. So then there will be a small performance penalty because of the compression at the compaction level. So apart from grouping smaller blocks together into 4K blocks, compaction will also try to compress if possible. Now let's have a look at a very simple scenario of compression and compaction working together. We have one volume called YVol. Inline adaptive compression and compaction are enabled. Now clients write the following blocks. One 8K block, which is compressible for 75%, two separate 4K blocks, which are compressible for 50%, and two 1 kilobyte blocks. After inline adaptive compression, the 8K block will have been compressed to 2 kilobytes. The two separate 4K blocks are not compressed because they don't form an 8K compression group. And of course the 1 kilobyte blocks are also not compressed. Then compaction is performed, and compaction will try to compress the blocks that inline adaptive compression has missed. So the two 4K blocks will be compressed to 2 kilobytes each. The two 1K blocks are untouched. And finally, compaction will form 4 kilobyte blocks for the consistency point to be written. And instead of writing 6 4K blocks, only 2 4K blocks will be written to the aggregate. So that will save quite some space, relatively. So for the record, if we'd only use inline adaptive compression, the savings would be a lot less, because we'd have to write 5 blocks instead of 2. You look at this command line example, you see you first have to enable data compaction. So you have to set it to true per volume. In this case, we set it to true for the YVol. Then after some time you should run aggr show efficiency and specify that you want to see the aggr compaction saved, volume logical used, and volume physical used. Now it will tell you that the aggregate Y data, in this case, has 45 megabytes of logical space in use. The physical space in use is a lot less. That's because of the compression. So in this case it's 28 megabytes. And the volume compression saved would be 19 megabytes, more or less. And the aggregate compaction saved would be 8.38 megabytes in this case. Now let's have a look at a practical example. For this demo I have two volumes in two different aggregates. The X volume is part of the X data aggregate and the Y volume is in the Y data aggregate. XVol has inline secondary compression and YVol has inline adaptive compression. As we discussed, secondary compression will give better compression, but adaptive compression will give you more benefit at the compaction level because the compression groups are smaller. So you will have more blocks that are less than 4 kilobytes. So compaction will function better with inline adaptive compression than it will with inline secondary compression. So we'll first enable compaction and then we will generate some I/O before we check the space savings. So the first thing is we check the settings as they are before we start. And we see that secondary and adaptive compression are set to true and they're also inline for the X volume and for the Y volume. Next thing we do is we make sure that both volumes are thin provisioned. So we set the space guarantee to none for XVol and for YVol. Then we show the efficiency savings and we will see that there are no savings. The aggregates are completely empty, or more or less, apart from some overhead, and the aggregate compaction saved is 0 bytes. So we're all fresh. Then we enable compaction for the X volume and we enable compaction for the Y volume. Remember, the one has secondary compression and the Y vol, the second one, has inline adaptive compression. Then we go to the Linux terminal and we go to the X vol and Y vol in both Linux terminals and we run some I/O. Again, this will generate 1 kilobyte and 2 kilobytes and 32 kilobyte blocks, as in the previous demo. And I edited the video. It would take some 35 seconds to finish the I/O. Then we look at the space savings, so we check the logical used, the physical used, and the compaction saved parameters. So what we see is that the compression of the X data is better than the compression of the Y data, but the space savings based on compaction are better at the Y data aggregate because of the smaller compression groups. And we're done. So what have we seen so far? Compression can be inline and/or post-process. There are two types of compression, secondary and adaptive. And in general, secondary will give you better compression results. And the reason for that is that larger blocks can be compressed. Secondary compression will need a minimum of 25 compression result to have it really compress these 32 kilobyte blocks. And adaptive compression needs a minimum of 50% to really compress 8 kilobyte blocks. The result of compression will give a difference in logical space used and physical space used. Compaction is a space savings technique that works at the level of the consistency point and will try to group multiple smaller blocks into 4K blocks when writing the consistency point. Compaction will give better results when combined with inline adaptive compression. And finally, compaction does not change logical data and it works at the aggregate level even though you enable it per volume.